Hello, students. So we've looked at simplifying many different mathematical objects. We've simplified fractions, exponential expressions, and rational expressions. We've also simplified radical expressions a little bit. We pulled out perfect square factors to make the radicands smaller. But what I want to focus on now is a concept called rationalizing the denominator. And it's something that we need to do sometimes when we're dealing with radical expressions. Let's consider 1 over the square root of 2. This has a square root in the denominator, and in general, we are not allowed to leave square roots in the denominator. The reason for this is actually historical. Back in the day, before they had calculators, they would have to do some of these calculations by hand. And if someone had to calculate 1 over the square root of 2, what they would do is they would look in a table of square roots, and they would see that the square root of 2 is 1.41421356 ... And if they wanted to figure out what 1 divided by the square root of 2 was, they could get an approximation by taking 1 and dividing it by 1.414213, as many digits as they wanted. But even if we take 6 digits here, what we'd have to do is we would have to move that decimal point 5 places to the right. And so here, we would have to move the decimal point 5 places to the right. And then we would have to put in an extra 0 and ask ourselves, how many times does 141,420 go into a million? And this ends up being an incredibly difficult problem to do by hand because the denominator has so many digits, dividing by it ends up being a real pain, and we do not like this. So in general, we don't want to end up with a square root in the denominator because actually doing that division, even if we're only picking a few digits to get an approximation, ends up being a lot of work. So we want to somehow change this so that we don't have a square root in the denominator. And there is a tool that we can use. We know that when we have a fraction, we can multiply the top and bottom by the same quantity. This is something that we've done before. And there is something that we can multiply by here to get rid of the radical in the denominator. And in fact, the thing we can multiply is the square root of 2. And the reason is because when we take the square root of 2 times the square root of 2, we get the square root of 4. And that 4 is a perfect square. So we can evaluate it, and we end up with 2. Now, if we multiply the bottom by root 2, we're also going to have to multiply the top by root 2. And then 1 times root 2 is root 2. So in the end, we end up with root 2 over 2. Now, this might not seem any better than what we had in the first place. We still have a fraction that has a radical in it. But having the radical in the numerator makes things significantly easier. If we wanted to figure out what this was approximately equal to without a calculator, setting up the division puts the 1.41421 on the inside and 2 on the outside, and suddenly this is an easy division to do. 2 goes into 1 0 times. It goes into 14 7 times. 7 times 2 is 14. We've got no remainder. Bring down the 1. 2 goes into 1 no times. Bring down the 4. 2 goes into 14 7 times. Multiplying gives us 14. Bring down the 2. 2 goes into 2 1 time, etc., etc., etc. This is an easier calculation by far to do than this, because dividing something by 2 is much easier than dividing by something with many, many, many digits. So in the end, this is considered simplified because we no longer have a radical in the denominator. This is called rationalizing the denominator because we're making sure that we no longer have an irrational number or a radical in the denominator. Let's do a couple more examples, and then we're going to look at one that we're going to do just a little bit differently. But the next two we're going to do very similarly. So let's take a look at simplifying 25 over the square root of 10. Now again, we don't want to have a radical in the denominator. That's going to end up causing a real difficult division if we actually had to do it by hand. So we're going to use our strategy of multiplying the top and bottom by something to get rid of the radical in the denominator. In the last problem, we took the denominator and multiplied it by itself, and in this case, it's going to work as well. In fact, this is always going to work because when you multiply something by itself, you end up with a perfect square. This gives us root 100 in the denominator, and the square root of 100 is 10. So by multiplying the denominator by itself, we end up with a perfect square in that radical that we can then simplify. In the top, we get 25 root 10. And there's one more thing that we can do here. 25 and 10 are both outside the radical, and so we can simplify that, and we can reduce those by 5. 25 divided by 5 is 5, 10 divided by 5 is 2, and we keep that square root of 10, so we end up with 5 root 10 over 2. All right. Let's look at one more that's just like these, and then we're going to look at one where we're going to use just a little bit of a different strategy. Here, let's look at the square root of 2/7. Now, this looks a little different. We have a fraction underneath a radical, but we can work on it the same way. And basically, we just want to split this up into root 2 over root 7. And then we can use this multiplying trick. What can we multiply the top and bottom to get rid of the radical in the bottom? In this case, it's root 7. When we do that in the bottom, we get root 49. In the top, we get root 14. And then we can evaluate the square root of 49. It is 7. And so we end up with root 14 over 7. All right. All of these problems worked out more or less the same. The thing that we were multiplying the top and bottom by was the denominator that we already started with. But I want to look at one that works out better if we do it a little bit differently. Let's simplify 15 over the square root of 18. Now we're going to do this problem twice. The first time we're going to do it just like all the other problems, and then the second time I'm going to show you a way that's a little bit less work. So again, we want to get rid of that radical in the denominator, and we want to multiply the top and bottom by something to get a perfect square down there, and that something is going to be root 18, just like all the other problems. Now when we do this, on the top, we've got 15 root 18. And on the bottom, we've got root 18 times root 18, which is going to end up just being 18. We could multiply these out and get the square root of whatever 18 times 18 is, but then we'd be taking the square root again, which takes us right back to 18. Now here, if we look at this, we notice that 18 contains a perfect square factor. 18 can be split up into 9 and 2. And then 9 is a perfect square. The square root of 9 is 3. So we've got 15 times 3 root 2 over 18. 15 times 3 is 45. So we get 45 root 2 over 18. And then 45 and 18 are both divisible by 9, so we can reduce by a factor of 9, giving us 5 root 2 over 2. That was a lot of steps. We multiplied by root 18 over root 18. We did that multiplication. We split 18 up into 9 and 2. We took the square root of 9. We multiplied the 15 by the 3, and then we reduced it. Let's see if we can find a way to do this with fewer steps. I'm going to rewrite 15 over root 18 again. And the thing that we're going to do differently is we're not going to multiply by root 18 over root 18. We're going to multiply by something else. We're going to multiply by root 2 over root 2. Now, why does that help us? Because in the bottom, 18 times 2 is 36, which again is a perfect square. While it's true that multiplying 18 by itself gives us a perfect square, that gives us one that's much larger than we need, which then causes us to have a lot of reducing that we have to do. If we can multiply it by a much smaller number and get a perfect square, that's going to be less work to do. Now in the top we have to multiply as well. That's going to give us 15 root 2. Now we can evaluate the bottom. The square root of 36 is 6. So we've got 15 root 2 over 6. And then just one more step, 15 and 6 are divisible by 3. When we reduce those by 3, we get 5 and 2. So we have 5 root 2 over 2, which is the same answer, but we got it in 1, 2, 3 steps instead of 1, 2, 3, 4, 5 steps. And we never had to deal with larger numbers. It ends up being much nicer. So if we can find a smaller number that we can multiply the bottom by to get a perfect square under the radical, that's going to save us some time and energy. And you will see some of those examples in the videos linked below.